Hello everyone, welcome in this video tutorial on modeling of disorder in crystal structure of a titanium 3 compound. Hope this video finds you all in a good health in these COVID times. The crystallographic programs used are SHELX2, SHELX and MERCURY. The necessary files required for the refinement are used with permission from Dr. Peter Muller and from Mr. Sonk Adlung. More detail about this particular example is available in this book, Crystal Structure Refinement, a Crystallographer's Guide to SHELX, edited by Professor Peter Muller. So before going to the refinement part, let's have a look at the expected structure. The only information available with us before the refinement is some Cp star titanium trifluoride is mixed with methyl aluminium and we are getting the green crystals where Cp star is pentamethyl cyclopenta dienyl anion. So let's start the refinement part. So let's start with the structure solution and the refinement part. So I'm selecting the .ins file. Okay, so the very first step is structure solution, and for this I am using the program SHELXT and I'm going to press the button solve. Now it is solving the structure. So from initial solution I am getting this model. So in this model the Cp star is clearly visible and the titanium atom is clearly visible and the rest of the atoms are not so good to understand. So I am going to first delete all the atoms except the Cp star ring and the titanium atom. Now I am going to select this atom and typing name 1, and then I am going to select all these carbon and type name 1, and I am going to sort. So the atoms are sorted in this way. So from the structure solution point of view, the three space groups are suggested. One is C2 by C, C2 and CC. Since C2 by C is the centrosymmetric space group, so it's a good practice. So first try in the centrosymmetric space group, and I'm going to do the structure solution and refinement in the centrosymmetric space group. Okay, let's come to the refinement part. I am applying the weighting scheme and put acta on to generate the zip file, and I'm going to refine with SHELXL. Good. So after the first refinement, let's do one more time refinement so the zip gets stabilized. Yes, now it's good. Increase the refinement cycle to 10 for the easy convergence. Let's the Q peaks little bit larger. Okay, now if I compact the structure, then what I am getting. Okay, so let's first look at the electron density peak. Now I can see the first 5 Q peaks are larger in the intensity, around 12 electrons, so it may be due to the aluminium, and then next 4, 5, 6, 7 and 8 peaks are comparable in the intensity. So these peaks may be due to fluorine and these peaks may be due to the aluminium. So I am going to assign the first aluminium and the fluorine. Okay, so I am using the slider to reduce the Q peaks in the Fourier map. Now these are the highest electron density peak, 8 and 5. So these 5 are of course aluminium, and these cubics are looking very symmetrical, and these 8 cubics also looking very symmetrical. So from the chemistry and symmetry point of view, we expect these cubics should be fluorine, but 8 fluorine are not possible. Otherwise the bond of titanium are much higher. So I am expecting from symmetry the 4 fluorine atoms, and these are the rest are aluminium. So let's make first these atom as aluminium Al. Then I am selecting 1, 2, 3, 4 and 5 and name L, name 1. So the atoms are named systematically. Then I am choosing the 4 highest electron density peaks, Q7, Q12, here is Q5, Q8, sorry, then Q11, Q6, Q10, Q9. So this one, this one, this one and this one. So these should be fluorine atoms. I am selecting the fluorine. Okay. So I am getting this model. So these cubic density in between the 4 fluorine atom may be due to disorder. We will see it later. So from here I am going to forward for the refinement. So I am going to select these fluorine atom and name 1, and then I am going to sort. So now I have titanium 1, aluminium 2, 3, 4 and 5, then fluorine 1 to 4, then carbon 1 to 10, and I am going to refine. R factor is now 47 and it is getting lower to 24%. Okay, so from here if I put the cubic off and grow the structure, I am getting a structure like this. A case compound is visible. So okay, so if I visualize the atom in some program like MERCURY, if I'm going to fuse first, and then if I'm going to edit the RES file, then I can see the aluminium atom 1 and aluminium atom number 5 are on the spatial position. They are only half occupied. They are actually on the crystallographic twofold axis. Okay, let's visualize by using some visualization program like MERCURY. So here you can see the structure. If I am going to see the only asymmetric unit, then it is looking like this. So if I display the symmetry elements, then since the space group is C2 by C, so it has a twofold axis, a C glide plane and an crystallographic inversion center. So here the inversion center is represented by dot, the circle, orange circle, the twofold axis by green, and the glide plane C is represented in the pink color. So now you can see the crystallographic twofold axis is passing through these two aluminium atoms, aluminium number 1 and aluminium number 5. These are on the crystallographic twofold axis and only half occupied. And this aluminium atom, you can see aluminium number 3 is on the glide plane, C glide plane. So from symmetry, you can see the aluminium 1, aluminium 3 and aluminium 5 are on the symmetry. Okay, so let's come back to the structure. Now, so aluminium 1 and aluminium 5, these are on the twofold axis and only half occupied. And aluminium number 3, here it is, yes, aluminium number 3, aluminium number 5 and aluminium number 1. So I'm going to select these So these should be in the part 1 of the disorder modeling. So I am selecting these atoms and type part 1. And now I am going to select the aluminum number 4 and 2, and I am typing part 2. So these are in the part number 2. Okay. So next, what I have to do, I have to set the free variable. So I am going to select part 1 by typing cell part 1, and I am assigning the free variable fvar to space 1, and then I'm going to select part 2 and I'm assigning the free variable fvar minus 2 space 1. So what I have done, just I'm selecting these atoms and press this button. So I am using the initial value 0.5 and the part 1 and part 2. So in part 1, the aluminum number 1, 3 and 5, and in the part number 2, aluminum number 4 and aluminum number 2. Okay. So now I am going to refine. Now you can see the R factor is around 21%. So if I putting the Q peak on, then you can see the Q peaks with intensity around 2 electron and around 1.5 electron, around 2 electron. These are around these fluorine atoms. So this is due to disorder. So how to model disorder? What I have to do, I am going to select these fluorine atoms and I am pressing this button split same, and now I am going to move these 4 fluorine atoms a little bit apart from the original position. Now that's enough. Yes, that's enough. Now I am going to press this button escape, and now I am going to select part 1 and free variable 21. Now I am going to select part 2 and free variable minus 21. So now you can visualize the atoms by pressing this button. So in part 1 and part 2, there are aluminium and fluorine. Part 2. So for part 2, the free variable is minus 21 and 21 for the part 1. Here you can see 20.5 because these aluminium atoms are on the twofold axis. They are not fully occupied, they are half occupied. So there is no 21.00, it is 20.5. Okay. So next step is I am going to refine, and the R factor is now 18% from 21, so it's good. So next step is done. If I'm going to edit the .res file, result file, edit res, I'm getting some Q1, Q2, Q3 and Q4. These 4 electron density are quite higher in the intensity, so these should be the methyl carbon. Okay, so these first 4, 1, 2, 3 and 4, these should be carbon. So I am naming them carbon. Good. So now I'm going to refine. Now the R factor is around 8.11%. That's nice. So you can see the maximum electron density is around 1.1 electron only. So now you can see the aluminium atom are disordered, the fluorine are disordered, but these carbon methyl are not disordered. Only the connectivity is disordered. The occupancy is not disordered. So next step is anisotropic refinement. I am going to type anis and then H add, then going to refine. So R factor is around 3.52 and all the atoms are generated. Now if I am looking at the INS file, the second free variable refined to 0.52, so 5248. So this should be practically equal to a 50-50 disorder. So we can refine it as a 50-50 disorder also. So refine one more time. Yes, now it's looking good. The shift is getting 0. That's okay. So now if I go to grow by typing grow, then this is the complete structure. You can see, and the R factor is 3.48%. The F observer is F calculated graph looking very nice. So structure is solved, almost it is ready. The 102 refinement will shift it to 0 value. So now the structure is solved and yes, it is solved finally. So in this way you can model the disorder. So if I am going to fuse again, so this is the asymmetric unit. Okay, so the second option is let's solve the structure in a non-centrosymmetric space group CC. So this is C2 by C. In C2 by C, all the thermal are looking very nice and it is a very good looking structure. The R factor is around 3.4%. Okay, if I'm going to solve the structure in suppose CC, so in CC I am getting this structure. So from the chemistry and symmetry point of view, these should be fluorine. So I am making them fluorine. These should be fluorine atoms, fluorine, and these should be aluminium, aluminium. These should be aluminium. Okay, so these are aluminium, and if I'm going to refine, put weighing scheme on, put ACTA on to generate the shift file, refine. Okay, so what I'm getting, okay, so the R factor is around 14%. Now these should be fluorine. So these should be fluorine, 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 and fluorine, and this should be aluminium. This should be aluminium. Okay, let's refine. These should be aluminium. Yes, aluminium. So these should be fluorine. Fluorine. So refine. Good. So now all the fluorine atoms are assigned except this one. So this is suppose C006, cell C006, and make it fluorine. Now you can see all the 8 fluorine are visible. I'm going to refine. Good. So as I know from symmetry, these should not be the 8 aluminium. These should be 4 aluminium. So 1, 2, 3, and 4. These should be in part 1, and the other should be in part 2. This one, this one, this one, and this one. These should be in part 2. I'm going to select part 1, setting free variable to 1. I'm going to select part 2, free variable -2 space 1. And if I'm going to refine, the R factor is around now 11%. So now you can see these fluorine are also disordered. The QP's electron density are appearing very close to the fluorine. So these fluorine are also disordered. So how to model the disorder? I am going to select all the 8 fluorine atoms. Okay, I have selected all the fluorine atoms. Now I am going to press the button split same. And now I am going to move a little bit from their position. Yes, that's enough. Now you can see all the fluorine are moved from their position, and now I'm going to escape, and now I'm going to select part 1 and free variable fr to 1 to select part 2 and free variable -to 1, and I'm going to refine. Okay, so now the R factor is further dropped to 7.7%, and the electron density maximum is 1.0 electron only. So next step is anisotropic refinement. Okay. Then next step is H-add. So the R factor is around 3.06%. Now you can see you are getting a lower R factor in the non-centrosymmetric space group, but the thermal of some fluorine are not looking good. So the space group centrosymmetric C2 by C, although have a little higher R factor, but it is the right space group, and you can solve the structure in the both group, but the C2 by C a centrosymmetric is more better in this case. So thanks for watching the video.